Alright, another draft physics video presentation. Sure, we'll play this Nick something or other Science Asylum video. Maybe I have attempted in the past to get him to do the conversation about physics thing, but this time we'll see. I don't know if I've explicitly offered him money before, so maybe I'll ask and see what happens. So here's a statement: all optics is scattering. Now it's an interesting title. And it kind of goes to this Einstein thing of equivalency principles, and I, for example, argue that things like the speed of force, that we have all these forces, all these interactions that take place at exactly the same speed. So why don't we just call it the speed of force instead of the speed of light, to better understand, that maybe all these forces are the same thing. And of course that's obnoxious to physics in the sense that they want to say bent space is completely different than magnets and electricity and light. Completely different mechanism. So there's a certain incompatibility that they'd have to deal with if they were to adopt that perception, because it would change perspective, right? It would put bent space more in doubt if this was the conversation, the speed of force, so this is sort of an important thing, what you do to these generalizations, and all this semantics gets really important. What words actually mean. Semantics in itself is a word. Maybe somebody doesn't know what that means. I'm just so used to it because of the internet. But yeah, it's just this whole idea of, what do words really mean? What is the real definition? How are you using the word? So in this video, he's really not arguing that all optics is scattering. He says it. But so what he's really saying is scattering means any interaction with matter. And so, of course, all optics is an interaction with matter. You can't have an optic without the matter. Just not practical. I mean, not accountable, not anything. Even if you believe in this ether crap, you have to have the matter to screw up the ether somehow to create some field through which the photon is going to have to interact. So it's a very, it's almost a silly description to say, that this would be scatter. Something goes in, hits something, and it leaves going exactly the same way it came in. And calling that scatter, when from my definition of scatter is you have to have a mechanism that is essentially ensuring that that there'll be divergence to the potentialities, that the scatter could be in any direction, even a scatter in the reflective sense, and that's what scatter means. Scatter means it might have gone this way, it might go that way. It just kind of depends on how you hit it. It goes a different way. So there's some variation in some guaranteed variation in what the expected output is. That's not some consistent thing that happens each time. It goes straight through. So I would say, obviously, all optics is not scatter. So anyway, he's going to say some other things that are worth commenting on, so I think it's worth playing the video just for just to observe how this argument is being presented. And yes, in 3 minutes and 56 seconds, which, again, I don't know if this is the best way to do physics, is in these quick little generalizations, these simplifications.
Welcome to the Science Asylum. I am Nick Lucid. What if I told you that everything in optics is actually...
He was actually pretty fat back then. Yeah, did lose a lot of weight. Well, not a lot, but he did tighten up a bit.
The same thing. No, seriously, all of it. Reflection, refraction, diffraction, dispersion, polarization, fluorescence.
So, I mean, polarization isn't an event. So, these are all events. Polarization isn't an event. Shouldn't even be in there. And whatever this flora blah blah blah, I guess that's the the compounds that brighten up when you hit them with energy. They glow.
Phosphorescence?
The same thing, really.
All the same! I'd say you were crazy.
Well, let's see, I'd say this is kind of funny and ironic, right? Because in the ones where I think it's obvious, where you try to do this equivalency thing, where you try to say everything is one thing, they won't do. But they will do it to the whole idea that everything is a wave. You know, that electrons are waving, that every, Volkswagens are waving, everything's a wave. They're willing to do it to that where it doesn't really fit. They're willing to do it, as I pointed out with the equivalency, Einstein's equivalency principle, that somehow all acceleration is the same, when clearly getting moved by gravity, which is pushing on your subatomic particles, and me hitting you with a hammer are not going to produce the same results. So why say they're equivalent? They're obviously not equivalent. I mean, it's just kind of, I'm just pointing out the irony of this. The idea that they seem to want to make things that are clearly different the same thing, and I'm arguing to make things that are clearly the same, the same thing.
Everybody just hear me out. First of all, what is optics anyway? Optics is the study of how light interacts with matter.
So that's what he called optics, but what he's really saying is scatter is an interaction with matter. So he's changed the word to mean that anything optical is somehow a scatter, when no, everything optical is some sort of interaction between this force stuff moving the speed of light and little matter bits like electrons and protons.
Without an interaction with matter, it's just
So, I mean, an interaction with matter. See, these kind of statements are, well, what does that mean, an interaction with matter? Does that mean matter like this piece of chalk, or does it mean, because this is with the hammer argument, right? The hammer is going to spread force over a certain area, and a lot of it over a certain area, right? Where, some other force, wind, could blow the whole piece of chalk, and disperse the pressure evenly across all the pieces of the matter. So there's clearly a difference. So just saying matter like chalk, or matter individual atoms, or matter electrons and protons, which one is the matter? I mean, see, they don't see any real need to always say it almost more generally, and never try to avoid talking about matter as being objects like the earth or the sun, when we know gravity is really affecting the atoms of the sun and the atoms of the earth, and more importantly, the electrons and protons are ultimately the things that are doing the moving. The atom itself as a whole doesn't do anything. The parts of the atom have to do something for the atom to do something. The individual atoms have to do something for the whole chalk to do something. To me, that's the kind of thing physics should be working on, is getting that language right, rather than this.
Electromagnetic theory. So let's say you shine some light at a glass surface. Most of the light will pass through. That's refraction. But some of the light will bounce off. That's reflection.
Yeah, and this is a kind of an interesting question. Is it the individual photons that are doing that, or, what exactly is happening? Does a whole photon reflect, or does pieces of the photon reflect, and then they're recreated into a photon, different photons? What exactly is happening? So this generalization is nice, but I mean, it's just kind of superficial. It doesn't explain anything about what actually happened when the energy hit the surface. What did the surface do? What did the individual electrons and protons do? And they really don't know, and they just won't say, well, we really don't know. I mean, I can give you a better guess than their guess, is all I'm saying there.
That looks like two different things to me. Sure, when all you do is stare at it.
Yeah, I mean, obviously they're different. And the fact that one of them will leave at an angle that's not consistent, and one will leave at a consistent angle.
Law of refraction is usually written something like this. These are called...
Right, so we know there's no law of refraction. That's our description of the function, okay? That there's rules to the function. And so we've defined some of the rules, but, these are just generalizations over what does a whole bunch of photons do. When we send a whole bunch of photons, what do they generally do? And so this law doesn't really say anything about the law of electrons interacting with photonic energy. It's not really that law. It's a law of a more general idea of what happens when I bang two pieces of chalk together. So they're not telling me the law of the interaction between the atoms of the one chalk and the atoms of the other chalk. They're giving me the law of big clumps of chalk.
Refractive indexes, which depend only on the material. A bigger change in N means a bigger deflection in the light.
So in the end thing really just has to do with a kind of density. So really you increase the density of the material, you increase the, you could argue the number of atoms you'll interact with, and the more atoms you interact with, you could sort of understand that if there's a slowdown in the speed of the force transmitting, because it has to do it through the pressure between the atoms, that you can understand that the denser the atoms, the slower the transmission of the force, because it's a little hammers. They've got to hammer each one of each other. They got to, where are the real hammers? Where's the real force, the push? And it's inside the electrons and protons of the atoms, and they've got to interact with each other. The different atoms have to interact with each other's forces to transmit. So yes, you have a different index number basically based on how cluttered the material is. The more cluttered it is with material, electrons and protons, the more dense the electrons and protons, the higher the N number.
But what happens when you apply it to reflection instead? The ends are the same, so they cancel, and now so do the signs, leaving you with this.
Right, so this is almost a silly mathematical trick. We just decided that there is no index on the surface. So, which is sort of makes sense. The density on the surface is just electrons. That's the only thing that these beams of light, or protons, can be interacting with, and the density is kind of a consistent idea on a surface. So you always end up with the same result. But it's an even result, so you're just sort of saying energy in, energy out on reflection. And then transmission is an absorption, and that's a different process, and so the absorption takes a different path. And I would argue the path is sort of being dictated by the fact that the matter is arranged to a surface. The surface forces electrons to be on the outside, essentially, and so you have an orientation of the order, and so it is essentially the force, the binding force between the atoms that are deflecting the light. I don't know if I can draw it, but I will attempt to draw it. The basic idea is that there's always a tension into the surface, on the surface. So everything on the surface, has a tension to the other mass in the surface. So when you hit it at an angle, what's going to happen to the energy is it's going to be added to this energy. So the energy binding, which would always be towards the material, towards the gravity of it, the center of its mass, and it's going to combine those two vectors and give you some vector in between. So essentially the amount of material will tell you how much gravity there is, so to speak, how much these atoms are connected to each other, and how much of an influence is going to be applied in this downward direction. So how much down you're going to add is just a reflection of how much mass you have that's pulling things together. It's almost like gravity. So you're almost just doing a gravitational equation in the sense you're saying, here's a mass, I'm going to apply energy, around them, towards that mass. Now, when it's exposed to the gravity, it's going to be exposed to it in this direction, and that's going to cause a bending. And it's essentially the same thing. Which way is gravity? If there's a force inside this material, right, which way is the force? Well, the force is in. The force is in. The force is in. So the force is down, in this case on this surface, and that essentially forces, when the energy hits the electron has a potential in that direction, a binding force, and you're hitting it with a force this way, and so the binding force and this force will be combined, and that's the direction that the energy, the photon, will move. When it moves this bit, which moves another bit, which moves another bit, but the bits will be moved in a new direction because of their own binding energy.
Which is just the law of reflection. They're the same. Oh, yeah.
So they're not the same. Clearly they're not the same for a very specific reason. One of them has to go through a bunch of atoms, and one of them goes through one interaction, or a small number of interactions. I mean, a reflection could be 2 deflections. It could be that it hits 2 electrons. It could be some other mechanism, but the point is it's not going through a bunch of medium. So they're fundamentally different in that sense. No point in saying the same.
Yeah? What about diffraction, smarty pants? Oh, that one's really fun. Diffraction happens when light spreads out after passing through small openings.
Okay, so now the light itself never spreads. So again, this is the kind of dangerous statements, right? That you're not really spreading the light. You're not taking a photon and spreading it. You're just saying, where's it going to go? So in a sense, diffractions would certainly be called a kind of scatter, because you can understand that the light comes in one way, all right, and because of what you put in the way, a slit for example, you've created a whole bunch of new potential paths. It won't be that the light takes all of these paths. It's that it has a potential to take one of them. Now, theoretically, if I did break this photon into something and recognize that it's a composite. So again, I've argued, they don't really tell you, is this a photon? That? Or is, do you need more of this to be a photon? What's a photon? They tell you no. I would argue that this is a photon, right? You need this. You need the whole thing. You need dot, 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 right? So obviously components of this, one bit of this, if you have to do waves, could go there, and another bit of the wave could be gone over here, and another bit of the wave could have gone over here. So different elements of this wave, the photon, all right, that has polarization. So let's understand it has elements that are here, and elements that are down here, and elements that are, spread out. And those different elements will end up going to different places. And, I would argue that clearly what happens is when they get to these other places, you have one of these little wavy things, pieces went here, and it combines with another little wavy piece that went there, and another wavy piece from another, from another photon, and you end up reconstructing a photon in a location. That's on phase. The ones that are out of phase, you won't make the right photon. You won't make one that's coherent or in any other way visible.
So it's all about spacing. A double slit like this has a spacing of about 0.7 millimeters.
Now, this is important, so, but it doesn't say anything about what the double slit does, which is kind of funny. So he points this out, but he doesn't tell us anything. So it's good to get perspective. So what they're saying here is the spacing, he means from the 2 outside surfaces, which is kind of funny, right? The arrows are pointing to the outside surfaces. So the entire experiment is 0.7 millimeters, almost a millimeter. And that would include the distance of the impediment plus the distances of the 2 openings. That total is 7 millimeters. So these 2 outside surfaces, by this mathematics, you can now figure out, thanks to me, okay, that those 2 outside surfaces are going to be telling you what the small bars are going to, what they're going to look like. And by that number, okay, so you're talking about 700 micrometers, and so that converts, okay, almost into 1200 wavelengths. So what you'll end up with is 1200 little bars if you were to go a full 360. So you're only going to see this part of the pattern, right? That's the only part that there's going to be enough photons for you to actually see. So you're going to see one little wedge of the pattern. And so that one wedge, if say it's 10% of the 180 degrees. And so 10% would mean you'll see 120 bars or something near there, you know, depending on, you know, if it's only 7%, then it'll be 50, that kind of thing. So those numbers fit perfectly with what I'm pointing out. Just saying.
700 micrometers. Even smaller, a diffraction grating like this has a spacing of 1.7 micrometers.
Right, now, so you see the trick there, right? Right? It wasn't that hard to notice that, oh, wait, they did this, change the goalpost thing. They, you know, they tore up the AstroTurf and put in regular grass. This is not necessary. This camera has an obsession with my crotch. I don't know what it is. No, stay on my face, please. Okay, you can do that. Well, or some portion of the body that's, you know. Anyway, I do have to organize my workspace better. All right, so you see what he did there, right? So he showed the double slit, all right? And he said, okay, so, and he did this distance from here to here. So he did this total distance. And now he's giving you the distance of one little opening. Right? So, you know, just little things like that. These are the gimmicks used to change perspective, to give people some idea of something, but isn't that just changing the game here? Because we know we do have two close surfaces here, you know, and they kind of ignored those. So he's saying the difference is 1 mm divided by 600. Yeah, so it's 1.7 micrometers, okay, and we know that, you know, a 1 is 1,000 nanometers. So you basically have 3. You can get 500 nanometers in there 3 times. So it's just 3 wavelengths. So the whole 360 degrees created by one of these slits would be, the fact would be is that you'd have a bright spot that would take all of this space and then one little node over here and one little node oh, wait a minute. Yeah, you have to multiply that by 2. There's 3 on each side, so 6 total. So I did that a little too extreme, but you'd have a big bar that would cover 20 degrees or more, and then you'd have a little bar here, and then you'd have a bar there. Alright, so that would be the pattern you'd end up creating with that opening. But the trick is, in the diffraction gradient, is that these are the distances you start measuring. So you have this distance, and then you have this distance, and then you have the next slit, and then you have this distance. So the distance gets as wide as the number of slits your laser beam covers. So if your laser beam covers, you know, 500 openings, you know, then you can figure that the widest one will be the how far apart that laser beam is. Basically, it'll be a huge number, like you know, 5 millimeters. Well, 5 millimeters. You know, I just pointed out before that, you know, 1 millimeter, almost a millimeter equaled, you know, 1,500. So if 1 millimeter is 1,500 bars, 5 millimeters, you know, would be whatever it is, 6,000 something or other, and 7,000 something. Obviously 7,000 of these little notches would become invisible. You wouldn't be able to detect them. You wouldn't be able to see any of that. Alright, so moving on to the next. See, but just there'll be no continuity between what he just did and anything. Yeah, he just didn't connect this to anything. So it was just thrown in there. And in a 3-minute and 56-second video, it's just kind of funny that he threw in, even in 3 minutes and 56 seconds, he had time to throw in stuff that didn't make any, seemed totally irrelevant.
But let's stick with the glass surface from earlier. Yeah, and how small is that spacing? Atomically small. A Dr. Natish Sharma actually...
So this is, Dr. Natish Sharma. So I have to find that, I suppose. But anyway, you know, again, we know that photons have to interact with something. So talking about how far apart atoms are spaced isn't going to tell you much, because the spacing is so tiny. But we'll get to that.
He handled this quite well in a paper from 2003. To make some sense of it, let's look back at that glass surface. Super zoom. These are two atoms that happen to be next to each other.
So the problem with this, okay, is that we know the average atom. So see, this is just another diagram that's a little bit deceptive. It just isn't quite what it should be. Not really going to illustrate the truth. It's going to, be helpful for their purposes, but it's not really going to get to the game. So they're saying 2 nanometer, 0.2 nanometers. All right. Well, we know that the average atom, by their own physics, is 0.5 nanometers. So that drawing can't possibly be right, because obviously they have it much further apart. So the 2 atoms have to be drawn like this, okay, to get 0.2 between them. So the atoms are big, okay, and the spacing between them is small. It's not that way at all. All right, so just for clarity. And again, the argument is why are atoms spaced? Well, they're spaced because the electrons are on the outside, and you're increasing the distance, the proximity. And so the protons, see, the further away you get, it's this inverse square law thing. So any attraction between this electron and this proton is much weaker than the repulsion between these electrons once they get closer. Now, when you go further away, it becomes less and less an issue, because your relative distance is so small, so large. When you start moving away, both forces are getting so weak that both of them become less relevant at the inverse square law. So the trick of the inverse square law is just proximity is really important. So the closer you get, you can get up to almost infinite amounts of pressure. So the pressure between the electrons, their hatred for each other, is really what's keeping these 2 atoms apart. And so these 2 electrons are communicating with those. This one's communicating with that. This one's communicating with that. This one's communicating with that. There's pressure between the electrons, and that's keeping the 2 atoms separate in the medium.
The light comes in and hits the atom on the left.
I mean, obviously these atoms are also sharing perhaps an electron. So they have an electron right here that both atoms are connected to. But again, they don't collapse into each other because all of these other electrons are repelling each other. And so the whole thing is kind of stable. So they can share an electron, and it's in a position, it's not spinning around anything. So this is another reason why you just can't buy all this physics. The stuff they established as their premises are doubtable premises. The whole the whole solar system idea of an atom, rather than the magnetic idea of an atom, where the little magnets are stuck in positions where they're in balance between 2 forces. Just if I stack 2 magnets on a stick with 2 similar poles facing each other, the magnets will levitate. That's the model they should have used. I think that's the more likely to be the right answer model.
First, the one on the right has to play a little catch-up, which puts it behind by this much. Then they each pass through, but now the one on the left has to...
So we know this doesn't matter, because exactly the opposite's going to happen when the light comes back out. So the catch-up argument doesn't mean anything. The real phase won't change any. It's only changed while it's moving through the medium.
Play catch-up, which puts that one behind by this much. See, light is a wave, and for it to...
So he said it. There's just absolutely no good reason to believe it. They just say it, keep hyping it, keep saying it. Light is a wave. So let's just understand the dependability of this stuff, right? I mean, he didn't draw the slit things in the right proportion. He didn't draw the size of the atoms the right size for the distances. All these little errors, and yet you're supposed to trust him when he tells you, we know this thing is a wave of some kind flying through space. A wave in a medium, like there's some medium, photon medium. And in the medium there's a bunch of things that are stuck to each other. So somehow if I move one of these little bits, I somehow influence this one, and I influence that one, and somehow light is moving through a medium that is movable. Like I can add extra pressure in one direction here, and I can somehow change where the little bits are going and the force. And I'm saying there's just no good evidence for that theory. There's no reason to believe light is a wave.
Exist, its parts have to line up at least a little bit.
So again, this is important too, right? It's parts. See, they have the idea that it's a composite particle, right? But they never say that. They just say photon, right? Everybody's used to this stupid language, photon. What does that mean? And he's just basically pointing out its parts. Yeah, which means, even if you believe it's a wave, it's clumps in the wave. There's clumps to it, and the clumps are defining the frequency, and the clumps are defining the polarization, and the clumps will tell you when you're in phase, two of these photons are in phase, or whether they're out of phase. But the phase part is essentially when you break the phase, you're not breaking the phase between two different photons, you're breaking the phase of the photon itself. You're taking this element and putting it here. And then if you're lucky, you'll take these two elements, and you'll move them back one, and then all of a sudden fix the photon, because now it'll be this, and this again.
Opposite parts line up, then there's no light.
So that, he puts a ball on there right now. Wouldn't that just solve the problem if you just put one on here, and you would realize that, when they don't line up, when they're on top of each other, and then there's no ball here, well, then the photon is broken, because now the frequency is broken. But if I can put them back in the right order, if I could take a ball here, and I could shove it back up here, and then I could have a ball there, and I could have a ball there, and I have a ball there, then I have a photon. That simple explanation works so much better.
That's called destructive interference.
So there's nothing destroyed. Let's understand, lots of experiments demonstrate the photons aren't really destroyed. They're only not seeable as a photon. The energy's still there, and you can recoup it. You can restore it to its original function. So again, all that happens is a photon interacts with something, right? And it I'll attempt to draw it properly. Okay, so you have your photon traveling through space. Now obviously it has a polarization, so I won't get into that, but obviously you can screw up its polarization too and then break it. But it's a thing, traveling, right? So you can screw it up by saying, I'm going to make this bit go this way. So it's not going to go the same way as these other bits. So then I got a hole here, right? So now this won't be seen as a photon, okay? Because it's broken, the frequency's missing. But I could have another photon somewhere else that sent something going this way, right? And that just ends up putting it here. And I fixed the photon. It's back to being a photon again. So a photon is just energy hitting a certain amount of atoms, and it's just really telling you how much energy is in the right order, right? How much of this, how much here, how much here, how much at this right timing cycle did I receive? So if there's only 2 in this position, well, it's only 2 photons then. All this other energy is still hitting the surface. All this stuff is still hitting, but it doesn't matter because only 2 were of the did the whole thing, did the required number of hits in a row, the 6 little hits in a row. Only 2 clumps of energy did it the right way. The rest of the clumps were not the right way, and so therefore they weren't registered as something that can be transmitted. There's still heat, okay? There's still real energy hitting the surface. They're just not going to be registered as a visible photon. They're not going to make it through the surface, and you're not going to see them on the other side. or they're not going to be able to be reflected.
Line up perfectly, then you get the brightest light. That's called constructive interference.
Right, but all there really is you break photons. You don't destroy anything. You break them. Parts are still there. You just broke them, and then you reconstruct. So it's just constructive reconstruction. You could say destructive disorder, but that's not quite right. There's disarrange. You can disarrange and then rearrange. Those are the two terms that you should be using instead of destructive and constructive. Disorder, order.
The space here is called the optical path difference. That difference needs to be a whole number of wavelengths.
So yes, again, obviously if I throw the parts, again, if I just throw photon parts, little photon bits from all kinds of places are coming at a surface, blah, 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 blah. I could just have this one, this one, this one, this one, and they're all going to converge on a surface. They're all heading a different path from it. The point is they have to hit this surface in the right order. That is, when it hits the surface, it has to be hit, then no hits, then hit, then no hit, then hit, then no hit. And this frequency has to be consistent, within a range, for it to be received by the mass, by the matter, by the row of atoms, as something that causes it to bulge or do whatever it does, to transmit the force completely, in a sense, undisturbed, unbroken, at its resonance. To create the resonant reaction, there has to be the right frequency of hits. The extra bits, I'm just saying, a certain percentage has to hit at this right timing. And if it doesn't, over the noise, then you don't have a photon.
So the wave lines up and you get light. The same thing.
So it's just parts, and then when they're in the right phase, they'll be seen as photons. Wrong phase, if they don't line up to be this phase, then you don't have a photon.
It has to happen with these two parts. The left one is off by this much, and the right one by this much. So the difference between them must be a whole number of wavelengths. Doing a little trig.
Yeah, it's just, all it's saying is you're just taking and recreating the order. They have to be in the right order. Okay, so it's just all this talk about all this stuff just to say, I can have three things. I can have the next three things coming in this way, and obviously they don't line up. Right? Or I can have them line up, and then the energy is magnified because now they're lined up. So it's a tipping point argument. You can just argue, that's why phase is important. Phase dictates the frequency.
We get this. Light will go everywhere that m equals 0, 1, 2, and so on.
So he says that, right? That somehow the atoms are sending images to those different locations. So it's scattering it to everywhere, theoretically, right? So he only showed where they constructively, or where they destructively, that's where they're going to be out of phase. Those lines still exist also. So they still exist as places that it could go. It just won't make a photon when it gets there because it'll be out of phase.
Because that's where constructive interference happens. Most of the light will go where m equals 0. But what happens?
So there's no reason stated for why most of the light does that. So, in the slit experiment you can understand why most of the light, goes to a certain location is because of the opening. So, he's going way too far here in terms of almost silly assumptions. So you could argue that obviously when you think of the slit experiment, you can obviously figure out that, the light that goes through the center is least likely to be affected by the surfaces, and the light that's closest, goes closest to the surface is the most likely. And that would be the reason why there's a lot more light here than there is over here, because it's less likely a photon goes here and here, and it's more likely a photon goes in all these places where it won't be affected. So you have more scatter in more misdirection, whatever, more directional change, whatever you want to. Obviously, the stuff going straight, well, there'll be a lot more of that, and there'll be less. The more you deflect, the less light is deflecting in those directions. It's harder to make a photon go that way than it is to make one go that way. Simple statement.
There. The D cancels out, and we can move some things around, which is just the law of refraction.
Right, so just again, more pretend there's no medium, pretend this, pretend all this kind of stuff, which, is just pretending. So it's kind of useless as a statement. It doesn't tell you anything about why the light scatters. I mean, there's a simple explanation. You make the slits narrower and narrower, you're more likely that the photon is going to be near the surface. The wider I make the slit, the less photons there'll be near the first surface. The narrower I make it, the more likely they are going to be near the surface. So, period. It's a perfectly reasonable explanation for why there's more deflection the smaller I make the hole. Well, yeah, because there's more likelihood that I'm going to be going right next to the surface.
In other words, refraction is just a kind of diffraction. Okay, I'll bite. Why is it all turning out this way? Glad you finally asked. If we look at this from an atomic level, in every case, light is absorbed by electrons in it.
So again, this is just a magical description of the reality. It doesn't have anything to do with any kind of real evidence that anything like that ever happens. That a single electron absorbs a whole photon. So what's really happening is the electrons are being affected by pieces of the photon. Pieces of the photon are affected by the different electrons or hit different pieces of the photon, and you're just sending pieces to these locations, and there are locations where you'll send the pieces where the phase will be correct, and so you have some hope of remaking the photon. Where the phase has now been broken, you have no hope. Even though the pieces are here, the pieces are in the wrong order. They're in the wrong frequency. So they can't make the photon. They can't make the thing we need. It won't be coherent. And therefore we can't see the energy. But the energy's still going there. Just as much energy that was going here. It's just you can't see it. Because it's not in the right form. It's not arranged properly. It's not connected. So it's all car parts. And the places where you put the car parts in the right order, that is, you put the bumper and then the hood and then the driver's seat and then the trunk, you got a car. But if the trunk shows up first and you end up putting the trunk in the front and then you put the steering wheel and then you put the hood, you're not going to make a car.
Atoms and then released again. We call this scattering.
There, so he said it, right? I mean, it's just such a statement to say that every time an electron interacts with a photon, there will be scattering. I would argue that there are electrons that are in very standard kind of conditions, where they can only move in one direction because of the way their tension is. So if their tension is even this way and can be made uneven this way, then the scatter, you hit them this way, okay, you can scatter them. I mean, they will move this way. And so you'll get a consistent movement. But if you hit them at some other angle, then you get an inconsistent change in direction. So the scatter depends on the condition of the electron you're hitting. So electrons on free atoms, that's kind of always going to be kind of scattered just because it depends on what position in the atom it is and which way it's going to go. So there's lots of variation. But atoms that are part of compounds have definite order to the arrangement of the electrons. And the electrons are in different geometry. And that geometry is going to require there to be a very consistent path for the photon to take. And that's why things are transparent, is because there isn't scattering. The force is very reliably transmitted. It might not be in a straight line, but it's reliably transmitted through the substance. So it's not all scatter. It's just wrong. Okay.
The only difference is how it's released.
Yeah, the only difference is how it's released, which is completely a difference that's completely affected by how the atoms are being arranged that you're hitting. The electrons you're hitting are connected to something, and how they're connected is going to decide whether there's variation in the potential for how the energy is going to leave. And sometimes there's a great deal of potential variation, and sometimes there's no potential variation.
Reflection is backward. Refraction is forward. Diffraction is forward, an example of which is refraction, or even back.
So this is, like I said, this is just sort of breaks all the vocabulary words. They're all specifically, they need more specific definition, and this just hurts the science rather than helps it to pretend that all these things are made of the same thing.
Backward, an example of which is reflection. Dispersion is just refractions for different wavelengths or colors, which...
Now, so dispersion is a kind of scatter. So that's a true scatter. Dispersion means that you did have choices and it went one of those choices, and yeah. So again, that's just wrong again. We know the atmosphere is scattering the light. Okay, so that's it's sending just as much back into space as it sends going down. It's you know, the light's scattering through the atmosphere. It's going in almost every possible direction. And of course, from every position, I can move 5 feet to the left and I still see all the light coming out of the atmosphere is still the same color, the same brightness. I can't move to some new position and find some new amount of scatter or a different amount of scatter. It's always the same scatter.
Gives us things like rainbows. Polarization is just refraction through a material that can only...
So that's, you know, this, they have no clue what polarization is. And again, they're showing all this jiggly stuff and waves going through the jiggles. Again, you know, if they really understood this and they understood that polarization is actual locations in space, that I fire a gun by moving my hand, keeping my gun parallel, and I just move my hand up and down. Well, the bullets I sent are now filling up space. They're filling up that space. If I move the gun this way, then they're filling up this space. Now, that's polarization.
Bond in one direction. Fluorescence is just...
You know, polarization is just, it's all antenna polarization. So again, you know, the connections are so clear, and I just don't know, you know, it's just so funny that people are just so hostile to these obvious connections. You know, for radio waves, there's a thing called antenna polarization. That is, your antenna is essentially dictating the strength of your signal. So your signal is very strong in this orientation, and so if I try to receive the signal with an antenna this way, I'm only getting a tiny percentage of the energy coming off of this antenna. But if I turn the antenna this way, then I have more likelihood of getting all of this energy. You know, I'm going to collect more of it. So it's polarized by essentially the orientation of the antenna. And the antenna basically works by the speed of light. The energy travels through it, and therefore the pulse information is essentially the wavelength. So if I get a big wavelength, I can have a very tall antenna and get all use out of all of it. But if I have a very small wavelength, I mean a very fast frequency, then I can't get very high up the antenna before I'm changing the signal. Therefore, this is the only part of the antenna that's of any use to me. And now when we talk about nanometers, 500 nanometer light, you know, then we're talking about just a little tiny antenna. And at the speed of light, how fast can the force move through an arrangement of atoms? So you have maybe 1,000 atoms or 500 atoms. The electricity impulse hits the atoms, and the atoms are producing the photon. And the photon, the first bit released, obviously has a head start over the last bit released. So the photon has, you know, a frequency, a distance between bits, and it has a polarization. So it's really just an antenna. The atoms in the crystal, okay, the metals are all crystals. That is, there's hunks, you know, connected to each other in kind of different ways, and on these seams is, you know, a very likely place for this electricity to happen, the antenna, and it moves across this seam, which has a disorder in it, where the two crystals are meeting each other, and it's likely the photons are being popped right out of that seam. And that's your polarization right there. And that's, your frequency is just the fact that it takes time to get from here to here. So it can all be understood as antenna polarization, and you're just realizing that very high frequencies have to be created on very small antennas. Perfectly reasonable explanation, just totally will be discounted as some sort of useless speculation, garbage, nonsense, rubbish. It's just amazing how you people really do hate science, don't you? We really hate doing the real scientific process, which is really look at the data and manipulate it as many ways as you can to see what it can do. You just don't want to test anything. You don't want to hit anything with a hammer and see if it breaks. You don't want to, you don't want to bend it. You don't want to twist it. You just want to look at it and call it a wave. Yeah.
Just when light is released at different wavelengths than it entered.
So yes, fluorescence. Okay, so yes, energy in, different kind of energy out. No big surprise that you can do some conversion. That you can have one kind of energy come in, heat, and you can create a different kind of energy out, light.
Phosphorescence is when light is released more slowly than it entered. In the end, all optics is just the scattering of light.
So he said it again as if it's true. It's not really scatter. It's really just this, all the light is a consequence of moving electrons, period. Electrons moving is the force transmitting information between electrons. And if you do it in such a way where you move the electrons in a precise, ordered way, they'll come at a frequency, and that frequency will be able to cause effects in atoms that will create things like electricity, and you'll know you have a different kind of effect. And again, it goes really just back to a simple argument that this is the photoelectric effect. You have an atom, you have an electron. The key to making this electric thing happens, that is where the atoms change their shape and become magnetic. The key to the whole thing is you're going to hit this electron. This electron is going to change its position. And the key is that if you give it enough time, it's under pressure with other things, and it's going to go back to where it was. But if you can hit it again before it goes back, then it's so far out, it'll go out who knows where. So it leaves. So if you can hit it twice, within a certain period of time, you kick it. You change the shape of this atom, okay, which is going to affect the other atoms next to it. It's going to transmit something called electricity, blah, 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 because you're creating essentially ions. You're essentially, a temporary one. It will be. But nonetheless, you're changing the electrical potential of the atoms by kicking electrons. And the kicking could just be you kicked it from this atom and you kicked it into the next atom. And the next atom said, I don't want it, and it kicked it to the next atom. So you're just kicking electrons. And so really it's just about this tiny little interaction. Just one electron being hit. And the idea is for a photon to be seen, that is for you to create enough of potential, you have to do that more than once to create another photon, something that's visible. You have to do that onto more than one atom at the same time, and then cause enough differential in the atoms to be able to transmit a movement of the atoms, or a movement of the electrons anyway. A net movement of electrons that's enough to be measured. And such.
Oh, how much is your mind blown right now?
Yeah, no, I mean, my mind's kind of depressed. This is just, first this whole cartoon attitude that physics has to be fun, and there's just no atmosphere in which you do your little performance You do your little trick as a lawyer, making an argument, and somehow though we never have the defense attorney. There's no opposing attorney to point out where you cut a corner, or you said way too much, or you said too little. It's just thrown out there as believe, and that's just not. That shouldn't be the scientific method. I mean, one of the scientific rules, along with repeating experiments and not cheating, like we have to say that. Oh, don't cheat. Don't inject the controlled rats with cancer. We shouldn't even have to say that, right? But beyond, this whole idea that you should repeat experiments and all this stuff, it should be one of the scientific principles is that you solicit testing and scrutiny, that you invite somebody to point out why that's not quite right or why there's a better answer. And they don't do any of that. They don't invite somebody to point out how, well, you drew all those conclusions based on a tiny amount of seems like evidence, right? It looks a little bit like, therefore it is like, I mean, it's just wrong to do that. Lots of examples. I mean, ostriches have wings, therefore they fly. These are conclusions you probably shouldn't be doing. They did fly at one time. When figures, though, right? Yes. Little things like that are just so proof of evolution kind of things, right? You just think about it for a second, and it's like, oh, fuck. What else would those stupid wings be for? Except flying. I mean, duh. Why are they there? It's like having somebody walking around with fins, actual fins, and you're just like, duh. Yeah, we're fish. All right, anyway.
Please share in the comments. And until next time, remember...
All right, well, I'll share something in the comments. I'll share an invitation for you to defend your physics against the critique you should be inviting. You should be saying, please show me how I might be wrong. Show me how my evidence sucks. That should be your whole scientific attitude would be, yeah, look, I'm Superman. Go ahead, bring all kinds of different rocks in front of me. Gold and silver and platinum and all kinds of stuff. Yeah, don't bring any of that kryptonite because, yeah, that is my weakness. But you should be inviting it, right? You got your little superhero suit on. You should be all set to say, we got it, we did it, we understand. Well, you should be willing to hear somebody say, maybe you don't, and this might be the reason why. Because you got this part wrong, and you drew that part wrong, and you're saying that part wrong. Why aren't you inviting it? All right. Please, if you have a counter-argument to anything I'm saying, please present it. But if the counter-argument is I look stupid, or I live in the wrong town, or I have the wrong politics, well, shove that right up your ass. Shit. Anyway. Till the next time and such. This is enough. So it is all, like I said, quite depressing. And I'll have to continue to endeavor to persevere. Damn it. It's not much fun endeavoring to persevere. Just a fact.